Okay, welcome to the talk, everyone. So I'm Jane. I'm assistant professor from the physics department, and today's talk is going to be about giant black holes in the center of galaxies tearing apart stars. I'm very excited to give this talk, particularly because as you know, the Nobel Prize in Physics this year has just been announced, and the prize have been given to three black hole astrophysicists, Roger Penrose for the discovery that the black hole formation is a robust prediction of general relativity, and also to two other scientists working on the galactic center physics, Andrea Ghez and Reinhard Genzel for the discovery of a supermassive black hole in the center of our galaxy. And also, you might remember a few months ago, the Shaw Prize in Astronomy this year has been given to Professor Roger Blanford, and especially for his contribution on black hole physics related to the jets and energy extraction mechanism from black holes. So in this talk, I'm going to be talking about black hole tearing apart stars, and I'll also, in order to explain that, touch a little bit of the physics that these Nobel Prize and Shaw Prize laureates are working on. So in the first part of the talk today, I'm gonna briefly introduce what is general relativity and also the massive black holes in the center of galaxies in our universe. And then we will jump into the topic, which is black holes tearing apart stars. And for that, I will give you a little bit about how the scientific discoveries are made and talk about what are the old predictions, what are the new challenges, and also what is the recent understanding on this topic. Okay, in order to be talking about general relativity, we have to mention Albert Einstein. So Einstein says the space-time around a massive object is no longer flat, but actually it is like putting a heavy ball on the top of a mattress. The surface of the mattress will no longer be flat, but it will be a dent or a curvature will be created due to the gravity of the heavy ball. So this is the same for space-time. When we have some heavy objects, especially astronomical objects, which are usually very, very large and heavy, the space-time around them will no longer be flat. And also the mass of the object and the space-time are going to be weaved together as predicted by general relativity. So if the mass of this object is too heavy and very extreme, so that it actually creates a singularity in space-time, then this becomes a black hole. And a singularity is basically a point that if any object or particle or even light particle get close to it, it is not able to escape from the gravity of it. And this radius or boundary of no return is called the event horizon of the black hole. So black holes sounds like an abstract mathematical prediction, but actually they have been observed in nature. And indeed, the prediction of the existence of black hole is the reason, one of the main reasons that Roger Penrose has been awarded Nobel Prize this year. So astrophysicists actually love black holes because they're very simple to study. We only need to use three parameters to describe their properties. And these parameters are the mass of the black hole, meaning how heavy it is, the angular momentum of the black hole, meaning how fast it is rotating, and the electric charge. But the electric charge for black holes in nature are going to become neutral very soon. So indeed, nature makes it even easier for us. We only need to describe a black hole with its mass and angular momentum. And such simple properties of the black hole also mean we can feed anything to a black hole and make it grow, but eventually what comes out is still this simple spherical-ish object. We can feed the black hole and make its mass grow using steak or dim sum or whatever your favorite food is, or in nature it's usually stars and gas. But what comes out is still a black hole described by some mass and some angular momentum parameter. And the most massive, the most heavy, the biggest black holes that we know exist in the center of galaxies. Nowadays, astrophysicists know that there is a very big black hole in the center of every big galaxy. So for example, this is an artist's illustration of our Milky Way galaxy. And nowadays we know there is a massive black hole in the center, and it is as heavy as about 4 million suns. And all the stars in this galaxy, including our solar system, is orbiting around the black hole due to the gravitational attraction. And this is indeed the reason that Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize. So how did they find there is this supermassive black hole in the center of our galaxy? So for this black hole, it is actually pretty dark and hard to see. And let me use a metaphor to explain this scientific discovery. Imagine we are sitting in a very dark ballroom and there is a couple dancing together. The gentleman is wearing a dark suit and it's very hard to see him, but we can see the lady in that dress who is spinning very fast and rotating. And therefore we know there must be a gentleman pulling her hand. And similarly, and these two scientists, independently with their group members, they have been observing the stars orbiting around the supermassive black hole in the center of our galaxy. And although it's very hard to see the black hole, but with the motion of the star, we can know there is a black hole there, and we can further constrain its mass. So let me show you a movie taken by the UCLA group led by Andrea Ghez using a very powerful telescope called the Keck telescope. So this team has been looking at the part of the sky close to the center of our galaxy for more than 10 years. And over 10 years, they take the images of the star. Let's see this again. And then they can plot the trajectory of the star. You can see some of the closest stars, like the one with the yellow orbit has even finished more than one orbit around that central point. And then after they have observed the motion of the stars, they using simple physics laws like the Kepler's laws, we can constrain the mass of the black hole to be about 4 million solar masses. And another very famous discovery that you might have heard lately is the discovery made by the Event Horizon Telescope team. So the Event Horizon Telescope is actually not a single telescope. It is a way of putting all the most powerful radio telescopes together into one. And in this way, we can greatly expand the baseline of this giant telescope and make it much more powerful than any single radio telescope. And using this new technique, scientists have observed the black hole in the next closest galaxy, which is called Messier 87. It is in the Virgo cluster. So luckily, this black hole is not that dark. It's actually quite bright. And it's actually also emitting a long stream of material, which is called jet, that we're going to talk about a bit later. And they have used this telescope for the first time, observed the shadow of the supermassive black hole onto the very hot gas surrounding that black hole. And using this, we can further constrain like the mass of this giant black hole and also test general relativity. So at this point, you might have some question in your mind. You might be wondering, like, why is this black hole so bright? Normally, aren't we say even light particles or photons cannot escape from the black hole, and therefore they're totally dark? So the reason that some of the black holes are quite luminous is because these black holes are active. There are some gas around the black hole and the black hole is eating that gas. So as gas falls into the black hole, they cannot directly plunge in. They have to be spiraling around the black hole due to the conservation of angular momentum. And they form some disk-like or torus-like structure, which is called a accretion disk. So because of the rubbing and friction between the gas particles in the disk, this disk becomes very hot, and hot objects tend to emit light or radiation, and therefore we can see the light produced by these gas particles right before they fall into the event horizon of the black hole. And actually, if we compare black hole energy production with the most efficient energy production mechanism, which is nuclear fusion on Earth, you can see black hole is actually very capable. So nuclear fusion has efficiency of 0.7%. And this means if you throw 100 Hong Kong dollars into the nuclear fusion plant, you can at maximum get $0.7 out of it. But actually a black hole usually has a 10% efficiency in converting the mass of gas into radiation. And in some cases, we can even have a efficiency that is more than 100%. That means if you throw $100 into the black hole, sometimes we can even get $200 or $300 out of it. So the efficiency of a black hole as compared to nuclear fusion is like comparing a modern car to an old-time carriage. And because of this reason, as black hole is eating gas and growing, it gives a lot of feedback in energy to the structure of the galaxy, and it can even affect the evolution of the galaxy and the universe. So here, let me show you one of the best simulations on cosmological studies made by the Illustrates team. And here we are seeing the very early phase of the universe. And you can see that these clouds are actually galaxies, and these galaxies can be merging together, and their central supermassive black holes can also merge in the same course. But at the same time, the galaxy is growing and the black hole is growing, and the black hole is producing a lot of light and throwing a lot of radiation and other forms of energy back to the galaxy. And therefore, it's very, very important for us to understand how these black holes work, and also to get a sense of the population of these massive black holes in our galaxy. So these days we can observe the galaxies and their central black holes using very modern telescopes like the Hubble telescope. But the problem is not all of these big black holes are very bright. So for example, the black hole in our Milky Way center is not very bright. We can only see the trace of the black hole by seeing the stellar motion around it. But this is impossible for the other galaxies which are too far away. So actually, more than 90% of the galaxies don't have a bright black hole. So how can we study these dark, really dark, big black holes and use them to understand the evolution of the universe? So now let's come to the topic, the theme of the talk today, which is tidal disruption events. So what is a tidal disruption event? So if we zoom into the central region of every galaxy, we can see that the stars that are orbiting around the black hole, they have very high velocity, and there are lots of such stars. So this is like creating a large hadron collider in the center of a galaxy. If you throw lots of particles with lots of energies, what can happen? Like occasionally one particle will collide with another. And in this case, sometimes the stars can have scattering between each other, and the trajectory of the star will be changed, and some stars can be scattered to get very close to the central supermassive black hole. And if the star gets too close, it can be torn apart by the gravity of the black hole. So the exact physics that is happening is the same as the everyday physics we see that is producing the ocean tides on the Earth. As you probably know, for example, when we look at the surface of the Earth, the side of the Earth that is closer to the moon is experiencing a larger gravitational pull than the other side, the opposite side of the ocean on the Earth. And therefore, the shape of the ocean is not spherical, it has elliptical shape on Earth that creates ocean tides as the Earth is rotating. And if you have seen the movie Interstellar, you might remember that there is a planet in that movie that is very close to a supermassive black hole. And because of the big gravity of that black hole, the tides on that planet is as high as a 20 or 200 meters. It's very strong. But here for our very unfortunate star that is getting close to the black hole, it is getting too close that the gravity becomes so extreme that the whole star is torn apart by this tidal force. So it can no longer hold a spherical shape. It becomes this long stream of stellar gas, and this stellar gas has some collisions with itself, and then eventually it forms this gaseous structure that we talk about called accretion disk around the black hole. And it creates a flare that can last for a few years that we hope to catch with telescopes. And this is called a tidal disruption event. So we can do some theoretical studies to know the property of such accretion disks. We know that they can be very hot. The temperature should be as high as 100,000 Kelvin, which is even much hotter than the surface of the sun. And we know that hotter objects will produce photons or light particles with more energy. And that means a temperature as hot as this should produce a lot of X-rays and ultraviolet emissions. And therefore, scientists have been using X-ray telescopes to be looking for these events of black holes tearing apart stars. For example, some of the best X-ray telescopes include the Swift Space Telescope by NASA and also the XM Newton Telescope by the European Space Agency. And one of the most famous X-ray type of event of this is called Swift J1644. And here I'm showing you is light curve, which means how bright it is over the days since it is discovered. And this event is so bright that it even outshines the whole galaxy by 100 to 1,000 times. And we know that this cannot even be the light produced by the accretion disks. So another even more extreme type of event is happening, which is called a relativistic jet produced by the black hole. So here as the gas is falling into the black hole, some other process is happening and a stream of highly relativistic material is ejected along the rotation axis of the black hole. And this stream of particles is moving at almost at the speed of light, and this is called a jet. And it is because we are looking directly along the jet, we see an extremely bright event. The physics of producing this jet is a bit complicated, but involves general relativity and especially some concept called ergosphere around the black hole. I'm not going into details here, but this is like a space around the black hole that nothing can stand still. You have to be rotating together with the black hole. And if we put a lot of magnetic field and gas into this region, then the black hole, if it's rotating, can eject this relativistic jet. And this mechanism is called the Blanford-Zinecki mechanism. And that is why Roger Blanford was awarded the Shaw Prize this year. Okay, so everything seems to be pretty consistent and pretty at this point. But a rule of thumb is that the universe never fails to surprise us. So as we see more and more these events and design more and more powerful telescopes to be looking for them, now here comes the surprise. So for a few events that we have seen, such as with the very powerful Pan-STARRS telescope in Hawaii, here I'm showing you the light curve of this event again. So you can see in 4 different optical wavebands, and then ultraviolet waveband, the event is very bright and evolving as the prediction. However, there is no X-ray produced from this event that we can see. And this is not a single event. Nowadays, the scientists have discovered a group of TDEs, or tidal disruption events, that only produce optical emission, but no X-ray. So how do we explain this? So there are 2 groups of ideas. One idea is to say, this is like a zoo and we are seeing different animals. So this X-ray TDE and optical TDE, they're really different types of animals in a zoo. And the other idea is to say, this is like in the famous Chinese idiom, we have the blind people touching the elephant. And because we are blind, we are not seeing the whole picture. We can only be seeing part of the picture. So it is still the same type of animal, just we are touching different parts or seeing it from different angles. So which one is correct? Now I'm very happy to share a little bit of my contribution to the field. So what do? So I do theory, but these days I mostly use very powerful computer simulations to do my calculations. And this is because the physics around black holes is very complicated. It involves gas and also light or radiation, and there are lots of magnetic field, and all of these calculations, they have been done in using the equations of general relativity. And therefore the calculations quickly becomes too complicated and too nonlinear to be done using pen and paper. So nowadays we have to write codes and run these simulations parallelly on hundreds to thousands of CPUs parallelly. And for example, I use some of the the fastest, largest computer centers in the world, such as the NSF Computing Center in the US, and also the Tianhe Supercomputer Center in China. In this way, I can generate movies showing the things that's happening around the black holes and compare that or use that to explain these observations. So let me share with you some recent movies that I have just made out of the oven. So here what I'm showing you is what's happening in this innermost part of the disk structure around the black hole. The black hole is right in the center of the movie. The left panel is showing what we see from side, and the right panel is showing what we see from the top. I'm going to start the movie. You can see different colors means how dense the gas is, and redder meaning the gas is denser, and black and blue means the gas is dilute. And these black lines with arrows, they're magnetic field lines. So we can see that the gas is spiraling around the black hole, it is falling into the black hole. And at the same time, not all of the gas can get into the black hole. A wind is also thrown from the black hole. A lot of this gas material is thrown out. And also you can see this dark blue region around the polar axis. And this is the jet region where we have lots of magnetic field and very few gas, but lots of energy. And this is consistent with the Blanford-Zinach process prediction. So using this type of work, I have proposed a unified model, which is basically saying that because from some angles, if you're looking along the spin axis of the black hole, there are not lots of wind or gas in that direction. So we can see the very hot accretion gas around the black hole, and then we can see the jet, so we can see X-ray emission. But if we are seeing from the side, and we have to see through the wind or the fog around this black hole, then the very hot photons are absorbed. What is left is optical emission. And this is like seeing a beast through a veil. So it comes back to the second picture that we are basically like blind people seeing elephant from different angles and therefore perceiving very different phenomena. Okay, last but not least, I want to say that the story is not conclusive yet. Right now, we are in this phase of under fast development of doing this type of surveys. We are seeing lots of tidal destruction events. We are seeing lots of supernova, which is how stars towards the end of their life, they have explosions and produce very, very bright flares. We are seeing a lot of gravitational wave events and their counterparts in the optical or X-ray wave bands. And their new and more powerful telescopes are continuing being launched. For example, the Vera Rubin Observatory, which is the largest optical outsky transient survey telescope, going to be launched within 3 years. And this telescope itself is going to allow us to detect hundreds of such black hole ripping star cases per year. And actually, the data that this telescope takes one night is going to exceed all the data taken by all the current telescopes so far on Earth. And also there are very modern X-ray telescopes like Eurosita being launched by European Space Agency, and also the Einstein probe, which is a X-ray telescope being built in China right now. And all these telescopes are going to allow us to observe many amazing astrophysical phenomena and use that to understand physics around the black holes, about the universe, and general relativity. Okay, so that's the end of my talk, and I would like to end at this summary slide. So as you have pretty much heard from the news and me at this point, black holes are predictions of general relativity. And we have at least one massive black hole in the center of every galaxy. And such black holes can rip apart stars and to be observed by telescopes. And from these events called tidal disruption events, we can probe general relativity and learn about many interesting physics about how black holes consume gas and produce radiation, produce energy and shine. And the frontier of this field, as well as many other fields in astronomy, are continuously being pushed forward by using the most powerful telescopes and the most powerful computer simulations in the world. Okay, thank you very much. Do you have any questions? Okay, if we don't have any question, then let's conclude the talk today.
Oh, actually, there's a question, Dr. Dai, but as a participant actually just sent it to me as a private message. Sure. So I'm forwarding it to you.
Okay. Not really, luckily.
Maybe you can repeat the question because I didn't share it with the public.
Oh, sure.
Share it with everybody.
So the question is, will the black hole in the center of our galaxy have one day its Earth, our planet, or the solar system? So I'm happily saying this is quite unlikely. So we mentioned that the stars in the center of the galaxy can be scattered to be approaching the black hole and got written apart. But our solar system, luckily, is in the outer skirt of the galaxy. It's in one of the spiral arms. And there we can just peacefully orbit around the central supermassive black hole under gravity. But here we don't suffer a chance of being scattered to get very close to the black hole and gets eaten by the black hole. Are there any more questions? And of course, if you have other questions about black holes, then you can always send me an email. You can find my profile on the website of the physics department. Okay, on that note, thank you again.